equivalent circuit diagram of the transformer. The last session we discussed how exactly we are transferring the resistance of one winding to another winding, finding out the total resistance referred to either primary or secondary. Similarly, you are also seeing that how to calculate equivalent reactance referred to the primary or a secondary winding. With that basic knowledge, just we'll establish the equivalent circuit of a transformer. So basically, why you need an equivalent circuit diagram? That is a question arises. That is, the equivalent circuit diagram of any device, either you can take any electrical machines, the equivalent circuit diagram that can be quite helpful in predetermining the behavior of the device. If you are representing circuit, then from the equivalent circuit diagram you can see the behavior of the devices based on predetermination of the different parameters such as regulation, efficiency and so on. Means equivalent circuit can be helpful for to predetermine the behavior of the device under various conditions. It is nothing but simply the circuit representation of equation describing the performance of the device. That is, we can represent these in the form of an equation and the circuit representation so that we can predetermine the behavior of the devices. Predetermination means without actual loading the transformer, with the help of the equivalent circuit diagram, we can analyze the behavior of that particular machine. The transformer having finite magnetizing current can be modeled or represented by an ideal transformer with fixed magnetizing reactance X0 connected across the primary. We have seen in the previous sessions that when the transformer drawn a current under no load condition, it has got two components. That is, one is I mu and another one is IW. That is, I mu is creating a magnetic flux in the magnetic core and IW is representing the core losses in the transformer. These two components, the I mu and IW, will taken care of in the equivalent circuit diagram. That is how to represent this. These two components are represented with the two parameters of the circuit. One is the R0, the other one is the X0. That is, X0 is magnetizing current component. That is to represent the magnetizing current. It is formed in the form of X0, which is connected across the supply. Similarly, R0 is also connected across the supply so that it is taken care of the core losses in the transformer. That is, the transformer core being subjected to an alternating field at supply frequency will have both hysteresis and eddy current losses and should be appropriately taken into account in the equivalent circuit diagram that is taken care by R0. That is that to take this into account, a fixed resistance of R0 is shown connected in parallel with the magnetizing reactance that was seen. Then the leakage fluxes voltage of this can be represented by a small reactance or the leakage reactance vector. The effect of winding resistance are also taken into account by the small lumped resistances. That is, one part is under no load condition. Under no load condition, it is represented by R0 and X0, which is connected across the supply. Then under practical conditions, then along with R0 and X0, you have to add R1, X1 in the primary, R2, X2 in the secondary winding. Therefore, I am writing here the different parameters are used in the transformer representation. that is R1 and X1. R1 and X1 are the primary winding resistors and leakage reactance. Similarly, R2 H2 are secondary winding resistors and leakage reactance. I naught is the no load current and I mu is the magnetizing current. IW is the working component of current which is responsible for the core losses in the transformer. With this nomenclature, just I1 and I2 are the primary and secondary current. Equivalent circuit of a transformer under no load condition. No load condition means we are keeping the secondary of the transformer open, then we are representing the transformer with the help of a magnetic core and primary and secondary winding, and under no load condition I told you it is represented by R0 and X0 component. It will take care of the core losses in the transformer. This will take care of the creating a magnetic flux in the core. This is how we have to draw the circuit for the transformer under no load condition. In the circuit form, once again it is represent the same thing with the V1, I0, IW and IMU, and this core is replaced by a simple binding of the two. Here the induced voltages are E1 and the E2. Now we have to see the equivalent circuit of the transformer on load. I told you if you are adding the circuit resistance and reactance on either side of the transformer winding, then it has become a practical transformer. That is, if you don't have a load, then there is no current is drawn, then there is no effect of R1 X1 and R2 X2. When there is a load is connected, definitely there is an impact of R1 and X1 and R2 and X2 on the performance of the transformer. Therefore, under load condition, ideal condition, one is this no load component you are added with the help of R0 and X0. Under load conditions, you are adding R1 X1 and the primary, R2 and X2 is the secondary. Then it is the total equivalent circuit diagram of the transformer. Just can see we are added R1 and X1 and this is no load component you are represented and R2 X2 is the secondary. Same thing can be drawn with the help of the circuit. Same R1 and X1. Here the no load component of R0 and X0 is connected across the supply is also represented. You can observe here the current drawn by the supply is I1. The current drawn by the supply is I1. The I1 which is flowing in both resistance and reactance of the transformer actually in this winding. Then the two component of I1, here I1 is here, then there are two components, that is I1 dash and I0. Okay, then the out of I1, I0 is only meant for creating a magnetic flux and the core losses in a transformer. It does not change its value unless until the whole supply voltage is changing, because supply voltage you are keeping constant. Therefore, the core losses in the transformer remains the constant and it does not change. However, this I1 dash will change as the load current I2 changes. Okay, the same thing is drawn here. This I1, I0, I1 dash. This is a primary winding, secondary winding resistance and reactance and the load. The voltage are terminal voltage V2, induced voltage E2, primary induced voltage E1 and V1. These are components. This is how we have to draw the equivalent circuit of a transformer on the load condition. Further, I want to simplify this particular circuit because circuit is now still it is isolated. The circuit is still isolated. I want one particular circuit for the easy analysis. Therefore, I want to transfer what I am interested is either I am transferring R2 and X2 to the primary side, or these all parameters can be transferred to the secondary side for easy analysis of a circuit that I want to do it now. Now that is why I am calling equivalent circuit of a transformer referred to the primary. Means what I am doing, I am transferring this R2, X2 load everything to the primary side by the transformation ratio. The how exactly you are doing this, you are already seeing how to transfer R2 and X2 to the primary side, or R1 and X1 is transferred to the secondary side. The same concept we are applying here. I am transferring R2 and X2 to the primary side. Then how further this circuit is reduced into the another circuit. See here, this is original circuit R1 X1, R2 X2, and this is the no load components of R0 and X0 that I am representing. Now my next step is, it is the equivalent circuit referred to the primary side. Therefore what I am doing here is, I am transferring R2, X2, load, I2, everything to the primary side, so that I will get only one circuit. How exactly? That is, we know that if you are transferring R2 to the primary side, you have to divide square of the transformation ratio. The R2 in the secondary, its equivalent in the primary is R2 by K square. You can see here R1, X1, V1 I am keeping as it is, same intact. There is I1, I0 as it is. Only thing is that what I am doing, R2 and X2 at the load, I am transferring to this side. Therefore, if you are transferring R2 to the primary side, it is R2 by K square. Similarly, X2 is transferred to the primary side, it is X2 by K square. Then, if you are transferring V2 to the primary side, it is become V2 by K. In the secondary, it is V2, its equivalent in the primary is V2 by K. Similarly, I2 in the secondary is equivalent to I1 dash in the primary. Then how exactly you are getting this V2 by K, I1 dash? I will show you here. Simple here. That is for this, how we are getting this. We know the transformation ratio V2 by V1 is equal to K. Therefore, if you are referring to the primary side, then you concentrate on what I want is V1. That is, V1 is equal to V2 by K. That is why you are getting here V2 by K. You are getting V2 by K. That is what I want is refer to the primary side. Therefore, V1 is equal to V2 by K. Similarly, the current you can see here. That is current. What is the ratio? I1 by I2 is equal to K. V2 by V1 is equal to K is the transfer ratio. If you comes to the current ratio, it is I1 by I2, that is equal to K. Then what I am interested? This current I want refer to the primary side. Therefore, how we are getting, that is I2, that is I1. V2 by V1 is equal to K. Therefore, how we are getting that? That is V1 refer to the primary side. It is V2 by K. What I am getting. Similarly, here if you are making I1 by I2, that is I1 is equal to K times I2. That is in this case V1 is going this side, K will come to the denominator. Whereas in this case, what I want is I1 is equal to, it is K times I2. What is a K times I2? K times I2 is nothing but I1 dash. Therefore, it is totally agree with all the circuit, that is here is I1 dash, it is I1 dash. I1 dash is nothing but also it is the refer to the secondary current refer to the primary side, and R2 and X2 is also refer to the primary side. Now the voltage across the load is V2 by K in the refer to the primary side. This is what we are calling as equivalent circuit diagram of transformer refer to the primary. Means simply we are transferring R2 and X2 to the primary side. Further, if we are simplifying that, what exactly we are doing that? We are getting equivalent circuit diagram R1 X1 R2 X square K2 by K square in the refer to the primary side we are transferred. Here this component I0 is very small. Then if you are shifting to the initial portion of the transformer, it does not affect much, and our simplification of the calculation is easier. Therefore, the assumption they are making, by shifting this, as such there is no impact of the circuit analysis. Therefore, this whole circuit, that is parallel circuit, is shifting to at this particular point and they are simplifying. Therefore, what they are exactly doing, they are connecting this R0 X0 at the beginning and now it is R1 X1 here and R2 by K square, K2 by K square. Now the current here is I1 dash, I am taking I1 dash here. The total current drawn by the supply is I1 and it is I0 and remaining I1 dash will flow here. Previously it is R1 and X1, the current will flow is I1, but by the assumption of shifting this, now the current is flowing R1 and X1 is I1 dash because I0 is very small. Now the circuit is very simple and it is easy to reduce it. Means you can add resistance, you can add reactance and you are getting one single resistance, one reactance. That is what you are calling as equivalent resistance of the transformer referred to the primary side and equivalent reactance referred to the primary side. The same thing I am doing here, just you can see here. I am adding those two, then what I am getting is RO1 and X1. RO1 is called as equivalent resistance to the primary side, it is called as equivalent reactance of the primary side. It is R1 plus R2 by K square, it is X1 plus X2 by K square. Further, if we are simplifying, further approximating by neglecting this component, therefore the diagram which is drawing here, what I am getting here is, it is the approximate equivalent circuit of a transformer referred to the primary side. This is how we have to draw the equivalent circuit diagram of the transformer referred to the primary side.